You were here yesterday, you know that we talked about this, which was an application of what people could call a midpoint rule for what we called a double integral in section 15.1. So I thought maybe we'd go through first the midpoint rule as it is in Math 170 or Math 175, and then go on. So if you look at my picture that's kind of crowded down in here, I have a sketch of the graph of y equals x squared, which is familiar. And of course you know how to get the exact area. You don't really need a computing sort of rule like Simpson's rule or the midpoint rule. So anyway, that's 1/3, which incidentally is 21/63. And you'll see why the fraction in a moment. So what would be the midpoint rule for a situation like this? You decide, first of all, how many base points you want to work with if you're doing any of these numerical integration schemes. That's equivalent in our example from yesterday about the temperature in Colorado to deciding how many rectangles you want to work with as the pieces. So to get something that I could do easily, I'm looking at 4 subintervals, and to get a good computing formula, you want to make them equal width, the same as these are equal areas. So say each of these original subintervals that goes with the black is 1/4. So I'm going to work with 4 rectangles. So if you do the midpoint rule, you first identify your 5 base points here. Notice it takes 5 of these base points to enclose 4 intervals. N intervals need n plus 1 base points. And then you take the midpoint after that, so that'd be an 1/8 and 3/8 and 5/8 and 7/8. So then I'm thinking of rectangles which are centered on these points in the red, and the height of the rectangle is the height to the curve. So then the Riemann sum that's approximating this area is the sum of the areas of these 4 rectangles centered at the red dots. Height is the height of the curve, which is this number square, because your curve is x squared. So with the 4 midpoints here, my Riemann sum then is 1/8 square, which is the height right there, times the common width. These all have the same width, 1/4, so I have it written once as a factor for all 4 terms. Then the next rectangle over, the height is 3/8 square. The next one, the height is 5/8 square. The 4th one, the height is 7/8 square. And these height times width products are areas of rectangles. And if you work that out, you get 84/4 times 64, and you cancel this 4, that's this 4 right here, into the 84, and you get 21/64 compared with your exact area, which is 21/63. So it isn't too bad, even for just 4 rectangles. So this is the midpoint rule idea for one variable, and then what we were doing to introduce the double integral yesterday was to look at this contour map that's in your handout, which the rest that you got yesterday or just this morning, and I eyeballed the temperatures then at the midpoint of each of my 16 rectangles. And what I was computing then with the double integral, f of xy would be your temperature reading at the midpoint. I'm computing the 16 readings times the area of the subdivision. And then if I divide that by the total area, I get the average of whatever this number is supposed to be reading, which would be temperature, which is what we went through yesterday. That was all these numbers here. But I think maybe it's a little more understandable if you see the same concept applied to finding an area, say, for one variable where that's more familiar. Okay, so then what the rest of today's class is about is the situation in trying to work these double integrals when your region is not rectangular, so you don't have just constant limits, but you have one of these odd-shaped regions, which you see in all the pictures. So look at problem 19. And you see what we have to do is use the limits of integration as the problem is given to figure out how the region works, how it looks, and then see from how it looks how you would write the problem with the reversed order. Because what they're asking you to do is to reverse the order and then get the actual value of the definite integral. In some of these problems, you could actually do the integration in the order as given, but in some of them you could not. Just for instance, looking at this one, you see in the order that's given, it would want you to do e to the y cubed dy. Well, you can't do that. You see, because if you say u is y cubed, you don't have the y square here to make the du. And so this is an example, one where to work the problem you have to reverse, where it's pretty easy to see that you can't do e to the y cubed dy in the sense of finding the antiderivative. You can't do it in the sense of Math 170 or 175. You could always do something like this, you see. If you really cared, why, you'd probably use Simpson's rule, but. So anyway, let's start with 19. So you see what this is telling you, you have to look at what differential is written first to the left, that's y. So it's y doing this to that. In other words, you're running, think of the green arrows here, which indicate the order. Y runs from y equals 0, which is your x-axis. See, they all have their tails down here on the x-axis, and they're all ending on the line y equals x. So you're covering the region R, which is this triangle, first the green way, vertically, and in your book, you see you have a region like this where you're going from a constant limit to a variable vertically, so in the y direction, and then following that by going horizontally with the projection of the area on the axis that's named second, like the red. In some of the others, if you look at, well, something like, well, in most of these, they're giving the problem well, okay, here's one, where, say, in either of this one or this one, you're starting out first going horizontally from constant to variable this way as a function of y, or this one you're thinking of x as a function of y. So they call one way type 1 and the other way type 2, and it doesn't really make any difference which is which, but the idea is that one type, your variable is the boundary that you strike with vertical arrows, and the other type, the variable is the boundary you strike with the horizontal arrows. I'm not sure which type is which, so I'm not going to go there. It doesn't matter. If you care, look in the book. But I promise I wouldn't ever ask on a test, identify is it type 1, type 2, and then take points off if you get it backward. That's the kind of teaching that I think is totally worthless. But anyway, you can see that there are the two different situations. And so generally what happens in these, since they want you to reverse the order, is that you're starting with one of the situations and you're changing to the other. And you have to figure out how the region looks to know how to do this. So in this one, you're starting, see, y is your first variable, so you're starting then with vertical arrows if you want to think of drawing the picture. And your region is this triangle. And your second integration is always between constants. That'll be true with all these problems when it's a double integral, when it's two variables. And the constants will be the projection of your region on the axis that you name with the differential you write second. So this is going, all the arrows vertically all start at 0 and end on y equals x, and then the projection of the triangle onto the x-axis, which you named second, would be the red. So I've tried, I think I've been true to my colors here, I've tried to use the red for the horizontal arrows or the projection on the x-axis, and the green, one shade or another, for vertical arrows and projection on the y-axis. So what you could actually work 19, this one in the order that's given, or you can actually reverse the order. So if you look at this one as given, you could integrate sine y dy, and you'd get minus cosine, and then you'd go 0 to x in here. So then you'd have this x, and you'd have this minus sign from integrating the sine, and you'd have minus cosine of your upper limit minus at your lower limit. Cosine of 0 is 1. And then you can integrate, you notice this is the same finally as x times, see there's a minus here and another minus there, so it's plus 1 minus cosine. And then you can integrate the x, and then you can integrate x cosine x by parts. And you've all passed Math 175, so you don't have to write out integrating it by parts if you don't want to. You can, if you want to use your calculator or the table in the back of the book, or and just basically look it up, you can do that. And what you get for x cosine is cosine plus x sine x. If you take the derivative of this, you'll get back to that. And then put in your limits, and you finally get the number, and this is what the book says it is. So this is one where they want you to identify the region. They don't specifically say in 19 or 20 or 21 that you have to reverse the order if you can work it the way it is. These that are 45 on, they specifically say to reverse the order, and most of them you can't do unless you reverse it. Okay, suppose you look at 21. You have e to the x plus y. Remember that factors into e to the x times e to the y. And it starts out with x. So x is running from x equals 0 to x equals log y. Now, the thing you have to get is that x equal log y means the graph y equals e to the x. You're familiar with the graph if you say it this way. It's the same, this is the same graph, but you're not used to seeing it that way. So here it is. So whether you call this x equal log y or y equals e to the x, this is your graph. But you see, if you're starting out with x, then the arrows all run from x equals 0, which is your y-axis here, to this curve, where if you solve this for x, you take the log of both sides, and you then have log y is log of e to the x, which is x log e, which is x. So this is your region in here, and then your projection on the axis you name second, which would be the green up here, is from y equal 1 to up here, y equal log 8. You know it's that far because this is what the problem gives you. That's the only way you would know it. So, I've set it down here. The projection is y runs from 1 to log 8. So if you work this one, if you recognize that this factors like this, you can think of putting the factor with the y, since that's going to be what you integrate second, off to the left. You can write it that way or just think it, and focus your mind on the integral of e to the x dx, which is just e to the x, and put in your limits. So then you have e to the log y minus e to the 0. And then you have this other factor e to the y, and then the limits on y. So then if you follow me up to here, you see you have e to the log y, which is y, e to the y. Here's your e to the y, minus e to the y times e to the 0, which is 1. And then you can integrate this by parts. And you can actually do that if you want to, or you can look that up. The high-end graphing calculators would give you that. They'll do integration by parts. And of course, Maple will. And it may or may not be in the table in the back of the book. I'm not certain. But anyway, if you integrate this by parts, you can integrate e to the y, which is e to the y, and put in your limits and this is what you'll get. So, as I said, for those of you who are doing the written homework, Amanda isn't going to care in a thing like this whether you really sit down and integrate it by parts, by hand, or not. If you're using my math lab, you have to do whatever will please it. So meanwhile, unless you have a question, let's take a look at 21. Let's see. Well, I guess we did that one. Okay.
Is it 47?
So let's see. Do I want to go to 47? Let's see. What I guess so. And then 48's over there. Sometimes I lose track of just what order I have followed here. So, anyway, take a look at 47 now. Now with these, most of them you couldn't work unless you reverse the order, and they want you to reverse the order and then work it in the reversed order in all of them. So that's what I'm doing. So we start out, and you see we have the region where the y is first, so y runs from y equals x to y equals pi. So you'd be starting out with arrows that would be going vertically from y equals x up to y equals pi. So the region as I've drawn it, with the arrows as I've drawn it, go with what you get if you reverse things. Your region is still going to be this triangle. You use your original limits with the original order to decide how the region looks, which now in 47 is this triangle, since the arrows when they were going vertically all started with y equals x and all ended up here with y equal pi. And notice that actually you couldn't do the problem in the Math 170 sense in this order. The integral sine y over y or sine x over x is an integral that has a name. It's called the sine integral, and the symbol for it is SI parentheses, whatever's the variable, SI of x. You can work this with something like Simpson's rule from, say, the integral from 0 to various choices of numbers. Or you could use your midpoint rule, except it would be less accurate. And so people worked the integral out because the sine integral has applications, especially in geophysics, for example. But it's not something where you can play games like integrating by parts and get it back to sine and cosine and powers of x. You can't do it in the Math 170, Math 175 sense. So with this, if you're going to solve the problem, you have to reverse the order, having in mind that this is your region, this triangle. So if you reverse the order, then it's dx dy. So now if it's x, then you're covering the triangle the way my picture shows. The x then is going from the vertical axis, from x equals 0 to the line here, y equals x is also x equals y, you see. Guess I could put that in. It's the same line, but you're thinking of it the other way. So 0 to y, and then the projection on the axis you named second is the projection of the triangle down here, which I show you in the red, and that would be the 0 to pi. And, oh, wait a minute, no, it's the projection on the axis I named second, which is the y-axis, which is 0 to pi this way. So that's why it's green colored. Okay. Now, we can do the problem because first we integrate dx and we get x. And then we put in our limits on x, 0 to y. So then we have this factor and y minus 0. So then you have y sine y over y. So they cancel. Might not hurt to show that. So you see, you're doing that essentially. And so now you're integrating sine y. You can do that, that's minus cosine. Now you're putting in your limits. And so the minus is down here, cosine pi minus cosine 0, minus 1 minus 1, so minus minus 2 is 2. And that's what the book says it is. Just a second there. So do you see what I did with 47? I have a question on that. The key thing is that you have to take the problem that you start with and use it to figure out how the area, what the region of integration is. And after you know what that region is, then figure out how to write the limits if you're reversing the order. And these problems in this group in the book, from 47 through as far as I asked you to do them, at least most of them will not work in the order that's given, and they will work in the reversed order.
I have a question.
Yes.
Is that how it's given in the book there on top?
This is, I believe.
Okay.
I believe this is what
Okay.
the book has. I don't have it in front of me, but
Okay.
somebody who has the book, is this what it says?
It just looks strange, but that's okay.
Well, it is, of course, it is strange.
Yeah.
I mean, because most likely you never saw a double integral before yesterday
Right.
in your life, and never had thought about there being such things. So it is strange. Yes, Mr.
How
Moore.
do you know that it would follow that triangular shape if it's y equals x, y equals pi?
Well,
That.
the order here tells you that these limits, whatever they are, refer to this variable. Okay, so then taking this as the name, y, it's y equals that. Well, what is that graph? This is the graph y equals x. That's where it starts. So all my arrows would start on the curve that's named this letter equals whatever this is. Yesterday's class, where we worked in section 15.1, they were all rectangles. So instead of something like this, you would have had a number here. And yesterday's problems were all y equals, if it was dy dx, they were y equal this number to y equal that number. So the change from yesterday, section 15.1, to today, section 15.2, is y equal whatever this formula is, so that defines a curve. So my first picture, which I didn't draw, would have arrows that are all going vertically, starting on the green and all ending on y equals pi, which is a horizontal line. Then the second limits are always numbers, and they're the projection of the region that's defined from the limits that you have first.
Okay.
Now, next week, we get to do triple integrals, okay? So then you'll have limits on x, say, and then limits on y, and that'll get you a region in the xy plane, and then the third time will be numbers, be the z values, say, from 0 up to a surface, something like that. Unfortunately, that's as far as we go. Be grateful we don't live in any more dimensions than we do. Just a minute, and we'll go on. Well, okay, everybody's here, so I don't have to take attendance. I can remember everybody's here. All right. So let's go on now from 47 over here to 48. Here, actually, I've drawn the pictures both ways. So, with the problem as it's given, you see this says that the y's all run from y equals x, okay, that's your slanting line, up to y equals 2, that's your horizontal line. So you're covering the region with vertical arrows like these. And then the projection of your region on the axis you name the second is 0 to 2, which I'm indicating with the red. So as given, y runs x to 2, projection is the interval 0 to 2. And again, y equals x is the same as x equals y, which is how I think now when I cover the same triangle with horizontal arrows that all start at 0 and end on x equal y, and then the projection is on what would be the axis named second, which would be the green here, which would be the 0 to 2. It's probably easier to understand if you actually take the time to draw the region twice, once with the arrows one way and once with the arrows the second way. The earlier versions of Maple, and I'm talking really earlier versions, but Maple 6, 7 along in there, had a package that was either called Calc plot or Calc P. Was one of the other you could bring up. And for iterated integrals like these, it would actually make the drawing, and it would say it was a thing like this. It would draw the triangle and it would draw vertical lines, say if it was this problem, and then it would draw it again in the horizontal lines like that, which was very nice. It would really draw this for you. But the later versions of Maple don't have it. They changed the code enough that the Calc P package wouldn't work. Some professors at one of the schools in the eastern part of the country had developed that as a kind of a add-on for Maple, and then the Maple company changed things enough it wouldn't work, and they didn't pursue it anymore. But it was nice, but it, essentially, this is what it did, and so that's where I got the idea for my drawings. So, anyway, here's our reversed order. So then, you see you can do sine of xy. X is the variable, so the y here you're treating it the same way as if it were a 3 or a pi or something. So you get minus cosine xy divided by the y, which you're treating like a constant. And then you put in your limits, so that's going to give you a minus cosine, that's going to give you this 2y square, which you've just carried along, times minus cosine y square, when you put this y in there, over y, minus cosine of 0 over y. And of course that's a 1, and there are two minuses here, so it becomes 1 minus cosine y square, and then you have 2y, because you see you're dividing by a y here. So when you divide by this y into there, you get 2y. So now you're set up to where you can use a u substitution. If u is y squared, this is your du. So I'm going from here down to here and noting that with the cosine y squared 2y dy, I have cosine u du, and then I change my limits. If if the y square is u and y is 0, u is 0. If y is 2, then u is y squared is 4. So your integral of what would be cosine u du from 0 to 4 is sine of 4, remember that's 4 radians, minus sine of 0, which is 0. So this thing, this part, gives you the sine of 4. You have another part of this. You see, you have the 2y square times the 1 over y. So you have 1 times 2y. The 1 times 2y gives you y square, and 0 to 2, so you get 4 minus sine 4. If you had put this thing into Maple, just as a definite integral, it would have given you the 4 minus sine 4, and never told you anything about any of this, of course. So, any question here on 48 before we go on? Well, let's look at 49. As given, you see you're doing x from x equal y, which is the same as y equals x, and that's where you're starting, so your arrows are starting on the line. So that puts the triangle down here, not up here. And you're ending all of the arrows at x equal 1. So you're starting out with the horizontal arrows like this, and this region below the y equals x line, and then your projection on the axis that you name the second, which is the y-axis, is 0 to 1. And so if you're reversing the order, your arrows are going to go vertically from y equals 0 to y equals x. And So that's down here, y equals 0 to y equals x, and then your projection this time is on the x-axis, 0 to 1. So this is the version you're actually using in this integral. And then you follow that, and you see that you're integrating first with y, so you can move the x square off to the left if you wish to do that. You can write it that way, or at least think it. What you have to think is, this is what has the y in it, and you're treating the x like it was 2 or pi or any constant. So the integral of, say, e to the a times x is e to the a times x over a, where a is a constant. That's essentially your substitution, but you want to just memorize things like that. And so I get e to the x y over x, and then I'm putting in my limits, y equals 0 to y equals x. Notice you can't just throw this away. So when you put in the x for the y, you have e to the x square over x minus, you have e to the 0, which is 1 over x. So now all this gets multiplied by this factor, and then that all gets integrated with x. So notice this x cancels, so you get x e to the x square, which you can do with u substitution. The x squared times 1 over x gives you an x, which you can do. So you can do this one, u is x squared, and then what you have is du over 2. So you have a half e to the u du, and the limits are the same. If x is 0 and u is x squared, u is 0. If x is 1, x squared is 1 and u is 1. So these are the correct limits for the new variable, and then this one you can do with the original limits. And so this, of course, is e to the u from 0 to 1, and you work through that, and you can say your answer this way, or this is the way the book says it, but it's the same thing. So you can say this or say that. I'll drink some water. So let's take a look at this one. One thing I'm glad that the book has done, they have, not everything is a triangle. You'd begin to think from some of these that the only region you ever have is a triangle, but you see these next two, the 50 here and then the 52, it's something else. It's a region bounded with a parabola. And of course, in theory, you could have any kind of region. You could cook up a problem where you're working with part of a circle or any conic section or trig function or whatever. So if you look at this one, your region is defined by y's or vertical arrows, say all beginning on the x-axis at y equals 0, and all ending on the curve y equals 4 minus x squared, which is parabolic. And so the problem starts then with green arrows that all look like these, and then the projection of your region on the axis that you name second is 0 to 2, and you see that's right, because when x is 2, y is 4 minus 4 is 0. So that's where your parabola is down to the x-axis, and that ends picture. So if you're going to go this way, then you have to solve for x. So x squared is 4 minus y, so x is the square root of 4 minus y. And so now you can think your arrows are all starting on this edge and going that way. So in the reversed order then, they're going from 0 to 4 on the, well, that will be this, what you do second on the y-axis. They're going from 0 to square root of 4 minus y first. You'd integrate that with respect to x, and then y second, and then the projection on the y-axis is the 0 to 4. So my problem with the reversed order looks like this. You see, I'm integrating first with x, so I've separated all these factors with the y off to the left, just to keep it easier to focus your mind on what are you working with when you do the first integration. And so if you integrate here, you get x squared, and you put in these limits. So when you square the square root, you see that what you get, you have the half here. You have the e to the 2y over 4 minus y that you separated. The half came from integrating the x, which gave you x squared over 2, and I put the 2 out in front. And then I've replaced my x squared with the square root square, so with 4 minus y at the upper limit, and it's 0 at the lower limit, so I don't have to look at it. So then my 4 minus y cancels. And so what remains is not such a bad problem. It's the integral of e to the 2y dy, which would be e to the 2y over 2 times this 2 gives me the 4. And then I put in my limits, and that's what you want it to be. So you see, you can do these with other regions besides triangles. But it's always the same game. You have to start with what you're given and figure out how that region looks. And then after you know how it looks, then think, how do I write it so all my arrows, if I started with something where the arrows were vertical, how do my arrows run if they're horizontal, or the other way around? So let's end with this one. So if you look at 52, you see your arrows are vertical at the start because it's y first, and they're all starting at y equal this. Well, the question is, what is that? Y equals square root x over 3, so square, and then y squared is x over 3, so x is 3y squared. See, that's a sideways opening parabola, like that. And the y's start there and go up to y equal 1. So your region is up here above the curve. And so I have my green arrows like that. So knowing that's the region, then if I'm reversing the order, they're all starting on the y-axis and going to the curve, like the red arrows. So in the reversed order, which means x first, x goes from 0, which is y-axis, to the curve. Well, what is it? 3y squared. And then the projection on the y-axis is 0 to 1. So you see in this order, in this order, you could not do the problem. I mentioned this before, because if y cubed is u, you need a y squared to make the du, which you don't have. But in this order, you can do the x first, dx to x, put in your limit, and there's the 3y squared you need to make it work the second time as a u substitution. See, here it is right here. So then what you're going to have is the integral 3y squared e to the y cubed minus e to the 0. Well, no, it's not e to the 0. The x is what's 0, and so you put the 0 there, so that's just 0. So now you can do this as a u substitution. There's your u, and then this dy is your du, and you can change your limits, and so you're integrating e to the u, and finally you have e minus 1. So before we go, let's look at our maple. And I've done a couple of these, I think. We were looking at our maple yesterday. The double int command will do these. And let's see, we looked at problem 24, and if you get to the back of the second sheet of paper, you'll see it says Thomas 15.2. In general, the domain is not a rectangle, which I've spent the hour pointing out to you. I'm on the back of the second sheet of paper. It's the maple, no, it's not that maple, it's the maple that says double int.
Oh, okay. So,
Has anybody got here without the maple that says double int? Okay. So, then, the first one I did is number 19, which is on the board there. And as I say, the domain is a triangle. And so if you do double int x sine y with your limits, I did it with a capital D so it would print the problem, line 14. And then if you ask for the value, you get pi squared over 2 plus 2, which is what I have here. The only problem, of course, with that is it's fine, except you still don't know how to do it if you didn't know how. All you know how to do is type maple, but anyway, you can see that it will do it. So then look at 47. So let's see, we have that over there by the corner. So it's a triangle by, as I say, bounded by the lines y equals x, x is 0, and y equals pi. And so first I have this integral typed, line 16, and then the value is 2. If you reverse it, you see double int sine y, x equals 0 to y, and y equals 0 to pi. Line 18 is the problem with the reversed order, and you see the value is, line 19 is still 2. And then I've done 50, the parabola y equals 4 minus x squared on the right, and so you see that line 20 states the problem, and you have your value. Then if you reverse the order, I've entered it in that way, line 22, and you get the same value again, which you should. Okay, notice that what's next in the maple is the next section, which we'll be doing next week. So continue to bring this maple to class, because it goes for quite a ways in the chapter. So I guess that's all I have for today.